Welcome back to the Computer Lessons.
Laptop engineering is a relentless war against the fundamental laws of thermodynamics and physical limits of structural materials. Every architectural decision represents a compromise between desktop-class processing power and the mobility required for modern professional life. Every cubic millimeter inside a chassis is contested. The central challenge in mobile design revolves around thermal design power, or TDP, which dictates the heat a system must dissipate. While a desktop CPU can consume 200 watts, a laptop chassis restricts this to 45 or even 15 watts. Scaling performance requires extreme efficiency. Heat dissipation relies on rapid thermal conductivity from the silicon die to the external environment. Traditional heat pipes use phase-change liquid to move thermal energy, but their thickness creates a physical barrier to thinness. Engineers must balance pipe diameter against total chassis height. Modern high-performance laptops increasingly utilize vapor chambers instead of traditional copper pipes to distribute heat across a wider surface area. These vacuum-sealed flat plates allow for multi-directional thermal spread, effectively turning the entire motherboard tray into a heat sink. This maximizes the available cooling potential. To improve the transfer of heat from the processor to the cooling assembly, engineers use advanced thermal interface materials like liquid metal. Liquid metal offers significantly higher thermal conductivity than standard paste, allowing chips to maintain higher clock speeds. However, it requires specialized nickel-plated barriers to prevent corrosion. Airflow engineering in a slim chassis depends on high static pressure fans designed with liquid crystal polymer blades for rigidity. These fans must push air through dense radiator fins despite limited intake gaps. Complex fan curves are programmed into the firmware to balance acoustic noise against thermal management. Motherboard miniaturization is achieved through high-density interconnect PCB technology, stacking multiple layers of circuitry within a thin footprint. This allows components like the CPU, RAM, and power stages to be packed tightly together. However, this density increases the risk of electromagnetic interference and complicates the thermal layout. The industry shift towards system-on-a-chip architectures integrates the memory controller and graphics directly into the processor die. By reducing the physical distance between components, engineers minimize latency and power consumption. This integration is the foundation of modern efficiency, allowing for silent fanless designs in ultrabooks. Memory and storage are often soldered directly to the motherboard to save vertical space and improve signal integrity at high frequencies. While this enables thinner devices, it eliminates future hardware upgrades by the user. The trade-off between total thickness and modularity remains a controversial design choice. Power delivery in laptops requires highly efficient voltage regulator modules to step down battery power for the delicate silicon chips. These modules generate significant heat during heavy workloads, requiring their own dedicated thermal pads. Efficient VRM design is critical to preventing power-related thermal throttling during long rendering tasks or gaming. Battery engineering focuses on volumetric energy density, attempting to pack the maximum chemical energy into a thin, irregular shape. Lithium polymer pouches are often custom-shaped to fill every available void inside the chassis. Balancing battery capacity against the total weight of the device is a primary portable constraint. Power supplies utilize gallium nitride technology to provide high wattage and compact form factors. GaN chargers generate less heat and are smaller than traditional silicon-based bricks. This allows users to carry high-power charging capacity without adding bulk to their mobile workstation setups. Display engineering in laptops utilizes embedded DisplayPort interfaces to drive high-resolution panels through thin, flexible cables in the hinge. Manufacturers must balance panel brightness and refresh rate against total power draw. Every extra nit of brightness reduces the total battery life of the system during mobile usage. The hinge mechanism is a critical structural element that must withstand thousands of cycles while housing delicate display and antenna wires. Engineers use friction-based designs or geared hinges to allow for one-finger opening while preventing screen wobble. Proper hinge tension is essential for the perceived build quality of a laptop. Material science dictates the rigidity and weight of the chassis, with magnesium, lithium, and aluminum alloys being standard. These materials offer high strength-to-weight ratios, protecting internal components from flex and impact. Carbon fiber is also used in premium designs to achieve extreme lightness without sacrificing structural stiffness. Keyboard engineering requires a compromise between key travel and chassis thickness, leading to the development of scissor switch and butterfly mechanisms. Achieving a tactile typing experience in a shallow footprint requires precise dome engineering. Backlighting adds further complexity, requiring thin light guide plates to distribute LEDs evenly across every key. Modern trackpads have shifted from mechanical clickers to haptic engines that simulate the feel of a click using vibration. This eliminates moving parts and allows for a uniform click feel across the entire surface. Capacitive sensors track multiple fingers with high precision, enabling gestures for navigating the OS. Port selection is restricted by the side profile of the laptop, leading to the dominance of the USB-C and Thunderbolt standards. Thunderbolt 4 provides 40 gigabits of bandwidth for external GPUs and storage through a single cable. This allows thin Ultrabooks to transform into workstations when connected to a dock. Graphics performance in laptops is managed through software logic like NVIDIA Max-Q and Dynamic Boost. These systems shift power between the CPU and GPU in real time based on the current workload. This ensures that the thermal envelope is used effectively without exceeding the cooling capacity of the chassis. Mobile workstations utilize higher wattage components and larger cooling systems to maintain peak performance during professional tasks. These devices prioritize raw power over thinness, often featuring replaceable components and extensive port selections. They bridge the gap between a portable computer and a desktop for engineers. Ultrabooks focus on the ultra-low voltage processor segment, typically operating within a 15-watt power envelope for maximum battery endurance. These designs often rely on passive cooling or single silent fans to maintain a stealthy profile. Performance is optimized for burst tasks like web browsing rather than sustained computational workloads. Thermal throttling is the final defense against silicon damage, reducing clock speeds when temperatures reach dangerous levels. Engineers aim to delay this process as long as possible through efficient heat dissipation. The duration a laptop can maintain its boost frequency is a true measure of its engineering quality. The right to repair movement is challenging non-modular laptop design and glued batteries. Modular laptops allow users to replace individual components like the keyboard screen or motherboard easily. Balancing ease of repair with the thinness and rigidity consumers demand is a significant modern challenge. Audio engineering in laptops must overcome the lack of physical volume needed for deep bass and rich sound. Up-firing tweeters and down-firing woofers are carefully placed to use the desk surface as an acoustic reflector. Software-based digital signal processing is used to compensate for the physical size of the drivers. Webcam integration requires microscopic camera modules to fit within thin display bezels. This often restricts image quality due to the small sensor size and lens glass. Infrared sensors for facial recognition must also be miniaturized to fit alongside the standard camera and microphones. Software optimization for mobile power states utilizes hybrid CPU architectures with performance and efficiency cores. The operating system scheduler decides which tasks require high wattage power and which can be handled by low-power cores. This management is essential for achieving all-day battery life on a single charge. In our next instructional session, we move from the laptop bag to the human body, exploring the engineering of wearable tech. We will investigate how smartwatches and trackers pack sensors and batteries into even smaller form factors. The miniaturization journey continues as technology becomes personal.
Choosing a laptop remains an exercise in identifying needs within this landscape of physical and technical compromises. The perfect machine balances speed, weight, and price for your specific digital workflow. Do you prioritize raw rendering power in a thick chassis or total portability in an Ultrabook? If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching and keep learning.